The learning objective is represent the electron configuration of an element or ions of an element using the Aufbau principle. So here I'll be talking about what is an Aufbau principle, what is an electron configuration, why do we need to write an electronic configuration for an element. So let's start. Hello everyone, the topic is atomic structure and electron configuration. This is topic 1.5 and I have split this topic into two parts. So this is part 1 from the AP Chemistry College Board. Now we know a lot about atom. How does an atom look like? But initially there were different models given for an atom by different scientists. First model was given by Dalton, then Thomson, then Rutherford and then Bohr. So this was the last model, which was Bohr's model of atom. So according to this model of an atom, he said that there is a nucleus at the center of the atom and this nucleus contains protons and neutrons, and around the nucleus the electrons are revolving in certain orbits. So this nucleus, which has protons and neutrons, is actually positively charged and these electrons are negatively charged. So this tells the first essential knowledge of the topic, which is the atom is composed of negatively charged electrons and a positively charged nucleus that is made up of protons and neutrons. So we know that the electrons are revolving around the nucleus, but what is the energy of those electrons? How can we tell that which electron is revolving where? So we need to tell the address of the electron. So this address and energy is represented by the quantum numbers. So there are 4 quantum numbers which tells about these two factors. First quantum number is principal quantum number. Next is azimuthal quantum number, third is magnetic quantum number, and the last is spin quantum number. So we will be dealing with all of these one by one. Let's start with the first one. The first one is principal quantum number. This is also represented as small n. So I already told you that there is a nucleus at the center and the electrons are revolving around the nucleus. But as we saw in the Bohr model of atom also, that electrons are revolving in certain orbits. So these orbits are named to help in explaining that where does an electron lie. So n tells about that orbit. So the possible values of n can be 1, 2, 3. So nearest orbit, or you can say shell, to the nucleus is n1, and this is also called as k shell. Then comes the second orbit, which has small n equal to 2, and this is the L shell. Then comes the third orbit, which is n is equal to 3, and this is the M shell. So it goes on like this. First is K shell, then L, then M, then N, and so on. So n is equal to 1 represents the K shell, n is equal to 2 represents L shell, n is equal to 3 represents M shell, and n is equal to 4 represents N shell, and so on. So each principal quantum number corresponds to a shell. Now we know that the electrons are revolving around the nucleus in particular shells. Now let's see further. The second quantum number is azimuthal quantum number. This is represented as small l. Now, when we know the value of small n, which was principal quantum number, we can identify the values of this azimuthal quantum number. The value of azimuthal quantum number can be from 0 to n minus 1. For example, if small n value is 1, then the value of L would go from 0 to 1 minus 1, which is again 0. So it would be 0. If small n value is 2, then the values of L can be 0 and 1. Similarly, if small n value is 3, then value of L can be 0, 1 and 2. So it will always be 1 lesser than the value of n. Now, this azimuthal quantum number tells us about the subshell. Principal quantum number used to tell about shell. Here, this tells about the subshell. So what does this subshell mean? If the angular quantum number, which is also the azimuthal quantum number, that is small l value, is 0, then we say that the name of subshell is S. If the value of small l is 1, then the subshell is P. If small l value is 2, then the name of subshell is D. And if the l value is 3, then the name of subshell is F. And how does these subshells look like? For S, it is spherical shape. If P, it is a dumbbell shape. If it is D, then it is double dumbbell. You can see that there are 2 dumbbells here. So these are the shapes of the subshells. And if it is F, it is a pretty complicated one. So we will be dealing with only these 3 first, the shapes of these 3. Next comes, if the value of n is 1, I told you, then the value of L would be 0 and the name of the subshell would be S. And we would write it as 1, which would be taken from n, S, which would be name of the subshell. Similarly, if n value is 2, then values of L can be 0 and 1. So the subshells can be, for 0 it is S, and for 1 it is, the name of subshell is P. So we will write it as 2 would be taken from n, and then S would be the name of the subshell. Similarly, for value L value 1, it would be written as 2p. Then the third quantum number is magnetic quantum number, and it is written as small m subscript small l. So this is magnetic quantum number, which tells about the orientation of the orbital in the space. I have already told about shell, I have already told about subshell. Now comes the orbital. Now what does this orbital means? Now if the value of n is 1, I already told that value of L would be 0 and it would be written as 1s. Now the value of ml would be 0 because the values of ml goes from minus L to plus L. So here the value of L is 0. So it means that ml would be also 0. So the number of orbitals here would be 1 because here there is only one value. So number of orbitals is 1. If I am talking about small n value as 2, then the values of L were 0 and 1. And if the L is 0, it means that it is 2s. So for 2s again, the ml value would be minus L to plus L. Again minus L to plus L means again 0. So the number of orbitals here is again 1. If I am talking about small n value as L, small l value as 1, then the orbital designation or the name of the subshell would be 2p. So here ml value will go from minus L to plus L. It means that minus 1 to plus 1. So the values can be minus 1, 0 and 1. So the number of orbitals, you can count the numbers here, 1, 2, 3. So the number of orbitals is 3. It means that 2p orbital has 2p subshell has 3 orbitals. 2s orbital subshell has 1 orbital. Rest of the things we can also do similarly. For 3, the values of L can be 0, 1 and 2, and the orbitals would be 3s, 3p, 3d. Further, if we want to write the ml values, for 3s the number of orbitals would be 1, for 3p it is 3, and for 3d it is 5. So you can see here that if we are talking about s, there is only one orbital. You can see in 1s, 2s, 3s and 4s. So the number of orbitals is 1. If I am talking about 2p, 3p, 4p, the number of orbitals is 3. If I'm talking about 3d and 4d, the number of orbitals is 5. And if I'm talking about 4f, the number of orbitals is 7. So the values of ml can be from minus L to plus L, and we can find that how many number of orbitals are present in that particular subshell. So the last quantum number is spin quantum number, which is designated as small m subscript small s. This tells about the orientation of an electron occupying an orbital. Now we know that there is shell, there is subshell, there is orbital. Now in these orbitals the electrons are present. Now the electron, what is the spin of that electron? That is told by spin quantum number. The value of ms can be plus half or it can be minus half, depending if it is clockwise or anti-clockwise. So it can only have two values. It can be plus half or it can be minus half, and each orbital can occupy maximum of 2 electrons. So if we say that this is one orbital, then it can only have 2 electrons, and those electrons will always be in opposite directions. They will have spin either plus half or minus half. They both cannot have the same spin. So these quantum numbers are telling that where do the electrons lie. If I am talking about a particular element or atom, I can say that which electron lies where. We will be telling you more about it in the electronic configurations. So let's see a recap of the 4 quantum numbers. If I said that shell is n is equal to 1, that is principal quantum number tells about the shell. The azimuthal quantum number tells about the subshell. The magnetic quantum number tells about the orbital, and further the spin quantum number tells about the spin. So if n value is 1, the L value would be 0, because L value can only go from 0 to n minus 1. So for n is equal to 1, the value would be, L value would be 0, and ml would be 0 also, because the ml goes from minus L to plus L. Similarly, if n is equal to 2, the values of L would be 0 and 1. the ml values would be 0, and for L is equal to 1, it would go from -1, 0 and +1. And each orbital can have maximum of 2 electrons. That is why if we are talking about this one, this is only one orbital, so there are 2 electrons here. Here there are 3 orbitals, so they can have maximum of 6 electrons. So n is equal to 2 can have maximum of 8 electrons, and n is equal to 3 can have maximum of 18 electrons. Now let's see an example. Give the possible values of L, Ml and Ms for electrons having n is equal to 2. Now if n is equal to 2, the values of L can be 0 and it can be 1. Further, if L is equal to 0, then Ml can be 0 and Ms can be plus minus half. But if L is equal to 1, the Ml value can be plus 1, 0 and minus 1. And all of these can have maximum of 2 electrons and they can have any spin. It can be plus half or it can be minus half. So these are the possible values of L, Ml and Ms for electrons having n is equal to 2. Now using S, P, D and F notations, describe the orbital with the following quantum numbers. If I am saying that small n value is 2 and small l value is 1, then this orbital can be represented as 2p because L value is 1. So it can be written as 2p. Second option is if n is equal to L, then L value is 0, then what will we write for this? It would be 4s. Similarly, if n is equal to 5, L is equal to 3, then the value would be 5f, and n is equal to 3 and L is equal to 2, it would be 3d. Now, can you just see if 2d exists or not? 2d orbital exists or not? If I'm talking about 2d, it means that L value is 2 and L value is 2. Is it possible? If n value is 2 and L value is 2, is it possible? It is not possible because L value can only go from 0 to n minus 1. So it can only be value as 1. That is why 2p exists and 2d does not exist. Now we know that electrons are present in the orbitals and these electrons are revolving around the nucleus and they are having some energy. But how do these orbitals actually lie around the nucleus? So this is explained by n plus L rule. Now we know what is small n, which is principal quantum number. We know what is small l, which is azimuthal quantum number. The orbital which has lower n plus L value has lower energy. It means that if I am talking about 1s and 2s, for 1s the n plus L would be 1 plus 0, so it is 1. And for 2s it would be 2 plus 0 equal to 2. So it means that n plus L value for 1s is lower than that of 2s. It means that 1s is lower at the is lying at the lower energy and 2s is higher than that. If n plus L values are same, then orbital having lower n value will have lower energy. It means that if I am talking about 4s and 3d, for 4s and 3d the n plus L value, for 3p and 4s the n plus L value is same, which is 4. So which will lie at the lower level? It would be 1 which has the lower n value. So it means that 3p would have the lower energy than 4s. So this is the order in which you can actually see that how the orbitals are lying. Initially at the lowest level is 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, like this. So, but how do we actually learn it? It is not easy to learn the order like this. So there are some rules, or you can say there are some principles which actually help us in identifying this. So that principle is Aufbau principle. So what you need to do is you will write the levels like 1s, then 2s, then 2p, then 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, like this. And then what you will do is you will draw the arrows like this. This is showing here. So the first one in the arrow would be at the lower level. So here 1s would be lower, then 2s, then 2p, then 3s, then 3p, 4s, then 3d, 4p, 5s. So it would be like this. So the electrons are added one by one into the various orbitals in order of their increasing energies, starting with the orbital of lowest energy. It means that when we are writing the electron configuration of atom, we would fill the electrons in order of their energies, and it would be filled like this. First it would be 1s, then 2s would be filled, then 2p, then 3s would be filled, then 3p, then 4s would be filled. It would be like this. Then comes the Pauli's exclusion principle. According to this principle, no two electrons in an atom can have the same set of four quantum numbers. It means that if I'm talking about 2s, here both the electrons are having the same spin in the same orbital, which is not possible because they would be having the same set of quantum numbers, which is not possible. So this representation is wrong. The right representation is first 1s, the both electrons are in opposite direction, then 2s, one will be clockwise and another will be anti-clockwise, then 2p would be filled. So if values of n, l and ml are same, then the value of ms would be different because one would be plus half and one would be minus half. So this was Pauli's exclusion principle. Next is Hund's rule of maximum multiplicity. It means that no pairing of electrons starts at any of the degenerate orbitals until all the orbitals of the subshell contain one electron each with parallel spin. For example, if I'm talking about this one, 1s is filled, then 2s is filled. And if I'm trying to fill the 2p, as 2p has three orbitals, so one electron would come in each orbital first and then the pairing would start. We would be seeing more of it in the coming slides. Here you will see that if we will write the representation like this, 1s is filled, 2s is filled, and then 2p, pairing is done, and then the third electron goes to the second orbital, then this is the wrong representation. First we need to write one electron in each orbital and then we should start pairing of the electrons. For example, here you can see how the filling is done. So you can see here that 1s is filled first, both the electrons, then 2s is filled, and then 2p, you can see that one electron is put in each orbital, and then the second electron was put in each orbital. You can see now. Now the pairing has been done. So filling of orbitals is done like this. So the orbitals are arranged according to their energies, and then the electrons are arranged in these orbitals. So we will be seeing more in the second part that how do we actually write the electronic configuration of the atoms. Please like and subscribe to the channel Log Iota and press the bell icon